All right, so sort of to recap where what we've accomplished, I guess, recently through this video series is really substantial when you think about it. We developed a method to take the derivative of a sum of two functions, of a product of two functions, of a quotient of two functions, when you had a constant times a function. Heck, we also deduced a derivative for the derivative of x to any power, where n is any real number. We did the derivative of any constant function. That was just a horizontal function which had a slope of 0. Recently, we've even computed the derivative of sine and the derivative of cosine to determine the slopes of the tangent lines to the sine and the cosine function. So we've got a bunch of properties that allow us to work with sums, differences, products, quotients of functions. We've also now got a battery of examples working with functions that we're familiar with. The goal of this video and sort of the subsequent ones in this next series is to address yet another function of familiarity, in particular, the exponential function. So here, something to remember, e is just a number like 2.718, so on and so forth. It's sort of like pi in that it's a decimal expansion which goes on forever and never repeats. But the thing to think about is here, e is just a number. It happens to be a number which corresponds to a special exponential function, and what makes that function special will actually be on clear display here in this problem. In order to address this derivative, because actually, heck, let's just start computing the derivative. You know, like any derivative, limit as h approaches 0 of f of x plus h minus f of x over h. You could apply that in this case, and you would get limit as h approaches 0 of e to the x plus h minus e to the x all over h. Because, well, what is f of x plus h? Just plug x plus h into our function, which is e to the x plus h. What is f of x? Well, that's precisely just e to the x. So we've got this expression here. Now, in order to make sense of this expression here, we're going to need another limit over here on the side that I've taken the time to sort of articulate a computation of. So what about the limit as h approaches 0 of e to the h minus 1 over h? You might notice that as h goes to 0, the bottom goes to 0, and so does the top, because as you may recall, any number to the 0 power is 1. So e to the 0 power would be 1, and the numerator would be 1 minus 1. So 0 over 0 upon evaluation, but you know just because a limit evaluates to 0 over 0 doesn't mean you can't find its limit. A number of tactics could allow you to see it. Here I've shown the computation numerically, and as h approaches 0 from the right, with plugging in h's of 0.1 or 0.01 or 0.001, we get corresponding values out, as you can see, like 1.0005. That's really, really close to 1. So from the right, the limit appears to be approaching 1. From the left, negative 0.001. Well, that appears to be approaching 1 as well, because over here, the outputs are like 0.9999. So from the right, the limit e to the h minus 1 over h approaches 1, and from the left, the limit also approaches 1, so the limit is 1. Okay, now that limit is e to the h minus 1 over h, and when you look at the limit that we've got here, it kind of is similar, but it's not exactly the same. H is approaching 0, we've got an h downstairs, but what we have upstairs is not precisely the same as this. What we do have, though, is e to the x plus h. Now think about what that is. That's e times itself x times, and then e times itself h times. So if you sort of wrote that out using your exponent laws, that would be e to the x, e to the h. Because you know that when you take two exponents with a common base and you multiply them, you simply add the exponents. So e to the x times e to the h would be e to the x plus h. So we've written these two things to be equal. In fact, they are. And then what you see is, upstairs in the numerator, both terms involve an e to the x. So e to the x could be factored out, and you'd have limit as h approaches 0 of e to the x times, what's left over when you factor out the e to the x? You'll have an e to the h in your first term, factor away an e to the x from e to the x, that will leave you with 1, which is being subtracted away, and in the denominator you have h. And now you see e to the h minus 1 over h, precisely the limit that we looked at previously. The limit is as h approaches 0, which is precisely our situation here. This has a value of 1. And then as a final observation, note e to the x has nothing to do with h. So no matter what h approaches, in this case h approaches 0, but no matter what h approaches, e to the x is e to the x. So this limit is e to the x times 1. Anything times 1 is just itself. E to the x is the result. So long story short, when you're taking the derivative of e to the x, the result, simply e to the x. E to the x is precisely the function whose derivative is itself, crazy as that may seem.